Alright, so guys, we had done this practice problem a good little while ago. Y'all keep asking for me to send the rest of this answer key out, so that's what I'm going to do right now. So this is what it looks like. A couple things just to throw out at you real quick, just some reminders of things to keep in mind are these constants up here that I have up here at the board, at the very top, of the worksheet. This is the speed of light, and that is Planck's constant. Now, the first half of these have already been worked. They've been worked within a previous video as uploaded. I want to say a week, maybe 2 weeks ago, we uploaded that video on this. Please understand that in this, I'm going to roll through a little fast after a little while and get through it. Along with that, I figured since I got a little bit of time, I'm going to add this sheet that I gave you, we worked on this week in class. I want to add that answer key on here as well, just to add a little bit more stuff on there to help you out so that we can see. Oops, sorry there. I'll throw my calculator on here so everybody can see it. Let's dim that up some. So we're going to start on this. We're going to start on 7. So problem 7 says, calculate the total energy in 1.5 times 10 to the 13 photons of gamma radiation having a wavelength of 3.0 times 10 to the negative 12 meters. So in this, we've been given a wavelength. Now you need to formulate the plan in order how you're going to do this. We're given wavelength. Okay, so we're going to start with wavelength. And from there, we're going to move this thing from wavelength. And I want to ultimately end at energy. But in order to just do that, I can't just go straight from wavelength to energy. I must first go through frequency. So going back to what we said before, either you're solving for, starting with, or going through frequency. So in this case, we're starting with wavelength. We're trying to find frequency. So we're going to start with the speed of light equation, because that has wavelength in it. So speed of light equals wavelength times frequency. And from there, frequency is the speed of light divided by wavelength. So speed of light is a constant, 2.98 times 10 to the 8 meters per second divided by wavelength, which our problem gave us as 3.0 times 10 to the negative 12 times 10 to the negative 12 meters. And that'll be equal, so type that in the calculator. So just, sorry, I didn't mean to knock that there. So on this, so you can see how this thing's supposed to look, 2.98, remember the E, in parentheses, divided by 3.0 second, and that comma right above the 7 gives me the E, negative 12 equals, so we get an answer of 9.9333 times 10 to the 19th, and that is hertz, because that is frequency. Now from here, we can solve to find energy, because we finally made it here to frequency. Now we can go to energy. So in this case, I can go energy equals Planck's constant times frequency, which is equal to 6.626 times 10 to the negative 34 joule seconds times that frequency we just solved for. And 19 hertz. Hertz and seconds cancel, leaves me with joules, which is what I'm after. So we'll literally just take that number. This is what I do that gets me the different number than some of y'all in class. And a lot of y'all are like drove nuts by this, so that you all understand. All I'm doing is taking that answer, so that big long decimal there, times that to give me 6.5818 times 10 to the negative 14 joules. Now the important part of this is joules for one photon. So another word of saying that, joules per photon. In this case, I have 1.5 times 10 to the 13 photons. So guess what I need to do here? Photons are going to be on the bottom. I need to cancel that out. All I got to do is multiply this number by the number of photons. So 1.5 to the 13 gives me 0.9873 joules of total energy. So there's the answer to 7. Now let's move on to 8. Alright. Calculate the energy and frequency of red light having a wavelength of 6.80 times 10 to the negative 5 centimeters. So in this case, we're trying to find energy and we're trying to find frequency. This is set up to make things easy for you. We're just going to roll through. But a heads up, notice something here. That's in centimeters. You can't just use centimeters. You're going to have to convert that, okay? I'm not going to work through that conversion. You guys should be able to do that now. So I got to find frequency first. So speed of light equals wavelength times frequency. So frequency is equal to speed of light divided by wavelength. Speed of light is 2.98 times 10 to the 8 meters per second. That meters. That's why we have to do that conversion. We can't just leave that in centimeters. So we're going to do that conversion. I end up with 6.80 times 10. Oh, I'm at negative 7 meters. So 2.98 about that. So 4.3824 times 10 to the 14th. And that is hertz. So there's one answer. And then the second answer, these are probably the favorite one you guys have once you have frequency to solve this, because it's literally just Planck's constant joule seconds. I've ran out of space here, so I'm just going to leave it underlined like that and say that we're taking this number and plugging in here. Okay, so this number right here is all I'm going to do so that you can see this. I'll set the calculator right there. So there's that number we just solved for, times 6.626 second E 34 gives me an energy of 2.9037 times 10 to the negative 19, and that's joules. Okay? Hopefully you're getting that. Let's move on to number 9 here. Wavelength of green light from a traffic signal is centered at 5.20 times 10 to the negative 5 centimeters. So there's that centimeters again. That giveaway. Calculate the frequency. This problem's easy, more simplistic, nothing really that hard here. So we're dealing with speed of light equals wavelength times frequency. Frequency equals the speed of light divided by wavelength, which is 2.98 times 10 to the 8 meters per second divided by that wavelength, which is 5.20 times 10 to the negative 7 meters. That's what you should get once you make that conversion, proper conversion. If you're still struggling with that, go back to the video on those conversions and watch that. 5 5.7308 times 10 to the 14th hertz. So there's that. Okay? And then this last one here, this number 10, is kind of like those ones that we kept working on that sheet. Calculate the frequency of light that has a wavelength of 4.25 times 10 to the negative 9 meters. Identify the type of electromagnetic radiation. So from this, here's the data giveaway. They already give you the information that you're in need of to find out what type of electromagnetic radiation this is. So I'm going to leave that there because they give me the wavelength. But I'm going to go on and calculate out the frequency. So in this case, frequency is equal to the speed of light divided by wavelength. We've done that 1,000 times. You should know how. Just plugging in that constant of speed of light divided by the wavelength which was given. 4.25 times 10, negative 9 meters, so I'm good. Don't need to convert. Meters cancel, leaves me with 10 per seconds. So I just go in here. Let's see, negative 9. And I get 7.0118 times 10 to the 16th hertz. So there's one answer, but then the second one we got to worry about is this 4.25 times 10 to the negative 9. So let me write that down a second. So 4.25 times 10 to the negative 9. So in order for me to do this, I need the electromagnetic spectrum, which I'm going to flip over to real quick. So let's go, should be right there for me. So on this, like I said before in class, what we're looking for is in this, the data giveaway is right here, whenever we're looking, in wavelength. And it's in meters, so in this case I'm dealing with 4.25 times 10 to the negative 9. Find where negative 9 is, so it's right here, 10 to the negative 9. And remember, at that point, that's 1.0 times 10 to the negative 9. And it increases as I go to the right. So it's 4.25, about halfway between these two, just a little less. So yet again, this is one of those easy ones for you. Just fall straight up and you end up finding out that it is X-rays. So we can flip back. So there's one answer, and the second answer will be X-rays. Alright? Not too difficult for you. So, let's look at this problem, these problems now. Okay? And we are absolutely going to roll through these. Alright? I want to roll through these a little bit faster because you guys should pick up at this point how to do these. If you're not picking up on these, bring this sheet with you to class, not to class, but bring it to my class in the morning, and I'll help you. If you're in 5th period, you can bring it during second lunch or first lunch out in the cafeteria where I'm on duty. But sadly, that's all I can give you. Unless you can come in first period, I can give you some help there as well. So, how much energy is in a photon of light? It has a wavelength of 4.62 nanometers. Automatically, I'm going to look and say, I have to convert this to 4.62 times 10 to the negative 9 nanometers. Not nanometers. Meters, sorry. My apologies. So how much energy is in that photon? So energy is equal to Planck's constant times frequency. You got to find frequency first. So we're going to have to use the speed of light equals wavelength times frequency. Frequency equals speed of light divided by wavelength. So 2.98 times 10 to the 8 meters per second divided by that wavelength, which we were given, 4.62 times 10 to the negative 9 meters. Meters are cancel out. So it's the 62. So I get on here 6.4502 times 10 to the 16th hertz. Then from here I saw find energy equals Planck's constant times frequency, which that frequency is what you just saw for right there. So 6-point stitch joule seconds. And I'm going to have to do it like this, but this is a multiplication here, okay? Just because I'm writing it like this doesn't change the operation. Times 10 to the 16th hertz. Hertz and seconds cancel. So take that number, multiply it by Planck's constant, and we find it to be 4.2739 times 10 to the negative 17 joules. Alright, moving on to number 2. Calculate the total energy on 1.5 times 10 to the 13 photons of gamma radiation with wavelength 3.12 times 10 to the negative 12. So we're going to do the same thing we did up here to get frequency. So speed of light, wavelength, frequency. Frequency equals speed of light divided by wavelength, which is equal to 2.98 times 10 to the 8 meters per second divided by that wavelength, which is 3.12 times 10 to the negative 12 meters. It's good there. So we're going to end up with, let's see here, 3.12 negative 12. Negative is 9.5513 times 10 to the 19th hertz. Then from there I've got to find energy. So energy, and this is just for one photon, is equal to Planck's constant times frequency, so 6.626 times 10 to the negative 34 joule seconds times that wavelength, that frequency. Sorry about that. Frequency we just saw for 9.5513 times 10 to the 19th hertz. Hertz and seconds cancel. So multiply those out. Oh snap. Why did it do that? So energy 6.3287 times 10 to the negative 14 joules per photon. And my total energy will be equal to that times my number of photons that I have. And I get 0.9493 joules. Okay, there's number 2. Let's move on to number 3. Calculate the wavelength and energy of light that has a frequency of 2.84 times 10 to the 15th hertz. Alright, so this time we've changed things up. We are now calculating for wavelength and energy. I should flip that color. So wavelength and energy has a frequency of already given to me. So these are easier. So energy is equal to Planck's constant times frequency, so 6.626 times 10 negative 34 joules seconds times a frequency of 2.84 times 10 to 15 hertz, which will be equal to Jesus. 0.8818 times 10 to the negative 18 joules. So there's one answer, and then the second answer, we're trying to find wavelength. In that case, speed of light equals wavelength times frequency. Wavelength equals the speed of light divided by frequency, which is 2.98 times 10 to the 8 meters per second. By frequency, which is given us as 2.84 times 10 to the 15 hertz. So 2.84 to the 15th, give me 1.0493 times 10 to the negative 7. And that's meters, because hertz and seconds cancel. Well, boom, bada bing. Alright. Number 4. Identify the type of electromagnetic radiation from a photon of electromagnetic radiation with 3.62 times 10 to the negative 19 joules. If visible light, identify the color of light. Okay, so in this, you're going to pretty much do what we've been doing so far. Nothing's going to change in that case. You're going to end up, now I'm just going to spell out how this should go. You should have these worked out. You should be fine. If you have questions, you should ask me. If you don't know how to solve these problems, literally it's all that's been done up in here before them to get to what we're trying to get to. Anytime I'm trying to identify the type of electromagnetic radiation, I'm always looking for wavelength. So that's the key. I'm trying to find the wavelength. In this case, I'm starting with energy. So literally, what I will do is I will take, and this is literally my way of doing it, you got to do it this way. Energy equals Planck's constant times frequency. Frequency equals energy divided by Planck's constant. That gets you frequency. Then from there, you will go into the speed of light equals wavelength times frequency, and a wavelength equals the speed of light divided by frequency. Where did that frequency come from? That frequency came from over here. So the number you get from here, you plug in there. This is what you should get for the answer. 3.62. I'm just going to show you me punching it in on my calculator. Okay? If this will help you out any, I'll even zoom it in for you. 3.62, 10, about that, by Planck's constant. Oh, snap. 34. So there I have that frequency now. Now with the frequency, remember that we're going to go for the speed of light. We're going for wavelength equals speed of light divided by frequency. So speed of light, 2.98 to the 8. I'm going to divide that by that frequency I just solved for. So I get 5.45 let's try it out. I'm going to confuse myself. 5.4546 times 10 to the negative 7 meters, or 545.46 nanometers. Alright, now these are the two pieces of information I will use to jump into this electromagnetic spectrum, which I will give you, will be on the screen tomorrow for whenever you need it. So, I'm looking at 545.46 nanometers, okay? Remember what we said in class? Bravo, Maddie, you came up with the rule, we call it Maddie's rule. So in this, I see nanometers and I'm falling right in this segment. Why? Because right here's 500. Don't believe me, there's the nanometers. And so in it, I'm at 500, between 500, 600, about 550, 545, somewhere right in here where we're sitting. So we're looking at green light. If you have questions on that, come and ask me. We covered that in class. You should be getting a good feel for this now, guys. Should not be an issue for you. Let's go back to VGA. So we are dealing with green light. Okay. From here, you're going to do exactly the same thing. The only thing that's changed, oh sorry, let me zoom it back out. You're going to do exactly the same process. This whole process right here that you've done is going to be the same process you're going to do time and time again. So in this, let's see my calculator again. We will do 270 negative 19 divided by 6.626. Alright, from there, and then we go 2.98, second e to the 8. We'll divide that out by what we just got there. So I'm going to hit that second and that minus negative key. That ANS means answer. So that's the last answer it's pulling from there. So we get 4.013 3 times 10 to the negative 7. So 4.0133 times 10 to the negative 7. Those are meters, or 401.33 nanometers. Alright, so that's what we're looking at. Jumping back to the electromagnetic spec. Looking on here, 401 nanometers. Okay, so I automatically go to my visible light. I'm in nanometers. I end at 400, and right there on the edge of it will be 401, somewhere in there. So I remember I'm going to say violet because Roy, red, orange, yellow, G, green, Biv, B is blue, I is indigo, V is violet. So there's blue, there's indigo, there's violet. We're right in that violet range. We're ready, we're almost ready to go into that ultraviolet range. So we're going to break that and say that it is violet light. Okay. From here, we have exactly the same thing. On number 6, they're asking you to do the same thing. Well, I'm asking you to do the same thing. I wrote these problems. Okay? Exactly the same process. Only thing we're using are these energies. So the only thing that's changed here are my energy sources. So in this case, we deal with 2.62, 15, Make sure you can see that. If you're on a phone, I don't know if you can see it or not. Hit enter. There's the frequency we get. So then 2.98 by that answer. So now we're looking at (7.5364 times 10 negative 7 meters, or 753.64 nanometers. Now remember, always jumping for these numbers are not always going to be helpful for you. Always putting it in nanometers. We just do that and try to make life easier for you so we don't get mixed up like I did that day. So 753 nanometers. Let's look where I'm at on the visible light spec. The visible light spec right here at the bottom goes from 400 to 750. I'm just barely shy of it. I'm right outside of it, which will put me in infrared. Hopefully you can see that. We'll end up with infrared rays. Flip that back over. So we go to infrared rays. So that right there is the answer key for both of these worked out for you. If you have a question, please come see me. Guys, do not forget, this is not just about this math. You also need to know the concepts. What was taught today in class is absolutely fair game for the quiz. You can expect it to be on there. And we're not going away from it. We're going to be discussing that for a good little bit, but it's going to be some good discussions. It's going to be in depth. If you have questions, come see me.